So, in the previous lecture we defined two parameters, number of transfer unit and height of a transfer unit to design or to find or to determine the height of a column. So, we said that number of transfer units should be seen as the degree of difficulty in separations. In other words, if you want to purify a gaseous stream, say from 10% to 30%, 40%, then the entire absorption column can be divided into several number of units, and each units we achieve a certain degree of rectifications or separations. And then we came out with the mathematical expression for number of transfer units as some integral, which we simplify to say that this equals y1 minus y2, that is total overall composition change, over divided by the average driving force per mass transfer. So, in other words, if we have large number of transfer units, all it reflects that we have very small mass transfer driving force for a given separation desired. At the same time, if we say that this absorption column is equivalent to very fewer number of transfer units, we are trying to say here that the average driving force for the mass transfer is quite significantly higher there. All right. Similarly, we define height of the transfer units. Okay. So, if we have one absorption column divided into 5 number of transfer units, each transfer unit has a height. How much height we require to achieve a desired degree of separations, and height of a transfer units we also said that mathematically it was shown to be equal to or defined as the ratios of the flow rate, gas flow rates over mass transfer coefficients or volumetric mass transfer coefficients kg kGa. So, all it means that if we have large mass transfer coefficients because of say large Reynolds number, then we have the height of a transfer unit is small. We require only a small height to achieve separations or to improve this purity. Similarly, if we have a larger interfacial area between the two phases, gas and liquid, then we have a smaller mass transfer height STG, and the product of the two, number of transfer units and height of a transfer units, gives us the total height of the column. All right. Now, if you go back to that lecture, we obtained these expressions based on the gaseous phase. We did the species balance, or we wrote down the operating conditions, operating line for gaseous phase. In principle, it is possible to come out with the similar expressions for the liquid phase concentrations. All right. So, that means number of transfer units, height of a transfer units can be written for the gaseous phase. It can also be written for the liquid phase. One can also write it for overall mass transfer coefficient or bulk quantities. All right. So, in this lecture we will write down this number of transfer units, the height of transfer units in the different ways, giving us the same results, and then we will take a few examples. Okay. So, recall in the previous lecture we had NTG as dy over y minus yi from y2 to y1, and this is for assuming dilute solutions. A simplified case, we have dilute solutions, and we had HTG g prime over ky a. So, the total height of the column Z is a product of NTG multiplied by HTG. Okay. So, G signifies here the gaseous phase and T for the total height of the columns. Okay. So, Z NTZ into STZ, and we are saying that we can also write as NTL into HTL. So, in other words, this NTL can be written as or can be shown to be equivalent. Leave this as an exercise, just make an analogy between the gas phase and the liquid phase. One can also obtain this as x1 to x2 dx over xi minus x. So, see the difference, y minus yi, now we have xi minus xi, and that means we have neglected 1 minus x1 over 1 minus x2 as 1 for very dilute solutions. Similarly, this HTL, this quantity here, can also be written as L prime over kxa. So, notice this kya, That means we had a quantity here 1 minus x logarithmic average of interfacial concentration with the mole fractions. So, which has been taken as 1 if you assume it is a dilute solutions. So, in both ways, whether you work on the gas phase or on the liquid phase, we should be able to obtain the same results for the total height of these columns. One can also define this NTG and NTS2AG based on bulk concentration, that is Y star or capital Y star or X or capital X star. All right. So, all of this based on these bulk quantities, one can also obtain number of transfer unit and height of a transfer unit. So, if you recall that we have the interface and then the concentration drops, right. So, there is some bulk phase, then drops here, then in the liquid phase it drops, then we have this bulk phase here for the liquid, and we have this gas phase. So, we have Y, we have X, Y I and X I's. So, for given Y, if you recall, we can have X star, and for given X we can have Y star. That means, this one can also obtain as NTOG number of transfer unit as Y2 Y1 dy over y minus y star. So, notice here now we are using NTOG, O means overall. So, that means we have avoided working on yi interfacial concentrations, and instead of this we work on x star and y star, right. So, x star would be equilibrium concentrations as if the entire bulk phase concentration is brought to this interface in equilibrium with this bulk phase concentration. Similarly, we have y star for a given x. So, we can also define NTOG instead of NTG, working on y star instead of yi, or if you want to work on solid free concentrations capital Y to capital Y1, then this becomes dy y minus y star, all right, which means analogous to this we will have HTOG, which can be written as G prime capital KYA. So, this is overall mass transfer coefficient based on the gas phase, all right. So, even these two should give us the same result, Z equal to NTOG multiplied by HTOG. The difference comes here O through Y star or Y star and capital KY as overall mass transfer coefficients, all right. So, which means one can also define as NTOL multiplied by HTOL working on small mole fraction x star or capital X star, and then we can have overall mass transfer coefficient based on this liquid phase. So, several ways of there is a writing here for determining this height of a absorption columns. Z equal to NTG multiplied by HTG equals NTL multiplied by STL. That will also equal to NTOG multiplied by STOG. That will also be equal to NTOL multiplied by STOL. The idea is the same which we did in couple of lectures earlier when we are discussing this interface, that generally we want to avoid working on this interfacial concentrations yi and xi which cannot be measured. So, instead of working on yi and xi, we have y star and x star, or we have instead of working on individual mass transfer coefficients ky and kx, one can work on capital Ky, overall mass transfer coefficient based on the gas phase, or overall mass transfer coefficient based on this liquid phase. So, either ways depending upon type of problems or the quantities which are known or which we can evaluate, one can obtain this height of this column. The main idea is we must understand that it is an approach, right. It is an approach in which case height of a column or a column has been divided into several such small transfer units. Okay. Larger the mass transfer, larger the driving force, we have a small number of units, and larger the mass transfer coefficient depending upon the Reynolds number, height of a transfer unit is also smaller. So, that is the most your fundamentals and basic, you must understand the meaning of this meaning of this and definition, the mathematical expression which we obtain for NTG and STG etc. Okay. So, just to recap here, if you recall again we had K y capital A mass transfer coefficient as individual gas fill mass transfer coefficient plus m slope of the equilibrium curve k x a, and then we can write H T O G. So, this is definitions we wanted to point out here, that H T O G equals G prime k y a, or G prime over k y a, which is H T G over G prime plus m, and k x can also be written as k x a L prime H T L. So, H T O G one can also write as H T G, overall mass, overall height of transfer units based on the gas phase, equals individual H T G based on the gas phase plus m G prime over L prime. So, essentially you have multiplied by G prime both side of expression, m G prime L prime H T L. So, this is another way of writing this H T O G in terms of H T G and H T L. Similarly, one can also show that H T O L, height of a transfer unit based on overall this liquid phase, will equal H T L individual 1 over m L prime over G prime H T G. So, these are different ways of writing this. We take some special cases here, that as given in the text, dilute solutions, of course, we are discussing here, that N T O G we are writing as y 2 y 1. So, N T O Z overall mass, overall transfer units. So, this will equal dy over y minus y star. So, we do not have any other terms because we are assuming it is a dilute solutions. Now, if equilibrium curve is linear, all right, sometime it happens that over the concentration range equilibrium curve is linear. That means, we can write as y star m x plus c. So, we have the equilibrium curve which is linear or maybe linear over certain range. In this case, we can write down this equation of this curve as y star equal to m x plus c. Then if you want to draw this operating curve, which is y equals L by G x minus x 2 plus y 2. So, this is our operating curve, this is the equilibrium curve. One can substitute one from the another as y minus y star equals L by G x minus x 2 plus y 2 minus m x minus c. So, we are trying to evaluate this integral for N T O G at dy over y minus y star. We are trying to see if we can obtain an analytical expressions. So, in this case, when we have the dilute solutions plus the equilibrium curve is linear, then we can write y minus y star as this. You should be able to recognize that this is also a form of q x plus c. Everything is a constant here, x 2 m y 2 L by G ratios given L by G. So, we have y minus y star as q x plus r. Now, one can go back and integrate expression for N T O G to obtain L by G x 2 to x 1 dx, and we have q x plus r. So, actually instead of q x plus c, let us use q x plus r for all the constant y 2 minus c L by G x 2, that is here r here, new constants instead of c. So, we have L by G x 2 to x 1 dx by q x plus r. One can again integrate this to bring L over a q, all right, ln y minus y star at 1 over x minus, excuse me, as y minus y star at 2. So, here we have again L by G, all right. So, L by G q, this q comes after the integrations, and then when you substitute the limits and you go back and use this previous expression for operating curves to obtain y minus y star at 1 and y minus y star at 2, and this will also be equal to then y 1 minus y 2 L by G cube. Again you go back and substitute the previous equation from the operating lines. Then we have y minus y star at 1. It's a simple mathematics. As an exercise, you should try this. Y minus y star at 1 and 2 over ln y minus y star at 1 over y minus y star at 2. Okay. So, we have a simple expressions for a very special case when the equilibrium curve is linear, and we have the dilute solutions y 1 minus y 2 over y minus y star logarithmic average. So, that is your logarithmic average between 1 and 2. So, this is expressions one can obtain analytically for number of transfer units. All right. Height of a transfer units is HTOG equals G prime over capital KYA. So, this is your overall mass transfer coefficients. So, we have expression for NTOG and STOG. In this special case, Z product of the two, this will become G prime KYA into NTOG y 1 minus y 2 over y minus y star m between 1 and 2. Okay. So, we sometimes this same equation is also rearranged to obtain this G 1 prime y 1 minus y 2. So, how much amount of sulfur dioxide or the impurity is removed, this also equals capital K y A Z y minus y star m. So, this also very frequently encountered this type of expressions for a very special case where we have this equilibrium curve being linear and we have this dilute solutions. Okay. There is another very special case that if we follow Henry's law. So, if we have Henry's law and linear, that means we have y equal to mx. So, C being 0. So, if we have the equilibrium curve like this, okay, this also very when the intercept is very small or at a very low concentration, we have very small mole fractions in the gas phase, then we can write the equilibrium curve as y equal to mx. In that case, NTOG can be shown to be obtained as a big expressions y 1 minus m x 2. So, m is the slope of this equilibrium curve, y 2 minus m. So, we have x 2 and here we have, excuse me, this should be m x 1, 1 minus 1 over a plus 1 over a, okay, over 1 minus 1 over a, and a should be familiar that a is L by mg, absorption constant. Okay. This is not the first time we are using this NTOG. If you recall in our previous first 2-3 lectures when we talked about the cascades in series or the devices in series, we said that one can obtain the expression analytically. In that case also we had this similar expressions for number of devices and number of stages in series required for certain rectifications. So, it is a family of expressions and there also we define this quantity A. Similarly, for the liquid phase NTOG, if you write NTOL, one can show you should obtain ln x 2 y 1 over m x 1 minus y 1 over m 1 minus a plus a. So, this is we correct here, this is x 2 minus y 2 over m, 1 minus a plus a over 1 minus a, and both of the expressions in the literature or the textbook you will find there is a graphical representations. So, you can use this analytical expressions or you can use the graphs directly. Okay. So, this is what we have as a theory for today's lecture or last 2 lectures if you combine to obtain the height of a column given the operating conditions. So, very simple case, given gas flow rates, we know what is the composition of this gas at the inlet. To do this, we have been given a solvent, we know the composition of the solvent, and we have been asked to find out the height 1, diameter 2, and the liquid flow rates. So, if you recall, already we have addressed how to obtain the liquid flow rates. Liquid flow rates comes from the minimum solvent requirement, and then we take 1.5 times as in operating conditions. So, once we know the gas flow rate, we know the liquid flow rates, we know the two compositions, one can obtain all y1, y2, x1 and x2. Okay. But we should also go back and check the hydrodynamics, in the sense that since we have a counter current flow of liquid and gas, there should not be loading or the flooding. So, we are supposed to go back and use the classical that Eckert plot or the Pigford plot for packing or the loading and flooding in the packings. Okay. That will give us what should be the permitted gas flow rates per second per meter square cross sectional area of this column. So, from that we get G prime, G and G primes gives us the diameter of the column, and from there we can get gives us the cross sectional area of the column, and from that we get the diameter of the column. So, the height of the column is now the only quantity left. We know G, we know L, we know all the boundaries y1, y2, x1, x2. We know the diameter of the column, so that we know the velocity. Once we know the velocity, we can obtain mass transfer coefficients. You recall that given the velocity, we know the Reynolds number. Based on the Reynolds number, we can obtain Sherwood number, and the Sherwood number will give us what is the mass transfer coefficient in the gas phase or in the liquid phase. Equilibrium we have m, so we can find out also the overall mass transfer coefficients. So, we take this example to determine what is the height of this column based on the number of transfer units and the height of the transfer units. All right, so let us take this simple example to do the calculations. So, we have absorption column, and we start with the similar approach or the similar type of problems, where this flow rate of the sulfur dioxide or total flue gas is given to us 1500 kg per hour. This contains 10 mole percent of sulfur dioxide. This should immediately we should write y1 equal to 0.1, capital Y1 equal to 0.1 divided by 0.9 to obtain 0.111. Since this is 10 mole percent sulfur dioxide in air, we should be able to obtain molecular weight as 0.1 into 64 plus 0.9 into 28.8 for air to obtain the molecular weight or average molecular weight of this flue gas is 32.3, so that we can obtain this G in kilomoles. 1500 divided by 32.3 molecular weight equals 46.41 kilomole per hour. And once we know this G, we can obtain GS, solute free basis, solvent free basis, as G 1 minus Y1. This is our one inlet here, to obtain 41.77 kilomole per hour. So, we know GS, we know Y1. Okay. And now we have been told that 97% of the sulfur dioxide is removed. So, 97% removal. Once we know 97% removal, we have this end is 2, we obtain capital Y2 as 0.111 into 0.03. So, we are removing 97%, 3% is left, we have 0.00333. So, we know Y2, we know GS, GS will remain the same. All right. And now, we have been given a solvent which is water, pure water. So, we have X2 equals to capital X2 equal to 0. So, there is no sulfur dioxide in this pure solvents, and we have the exit concentrations, where we have this LS will remain the same, X1 becomes unknown quantities. So, LS and X1 are unknown quantities. We have the packings. So, it is a very standard type of problems which we addressed earlier also. PT equal to is given 1 atmosphere, temperature is given 30 degrees centigrade, and it is packed with 25 millimeter of ceramic rashing rings. Okay. So, as soon as we see this 25 millimeter ceramic rashing rings, we can go to that table and we can get the different information we wanted for this packing factor which we require to do this hydrodynamic calculations. This is also given to us that mass transfer coefficients Kxa is 1.25 kilomole per cubic meter per second per del x. So, notice this Kx, individual mass transfer coefficient based on the gas film is Kxa 1.25 kilometer moles per cubic meter per second per del x. So, check it is consistent with the definitions of mass transfer coefficients units, and Ky is given as 0.075, this for the liquid phase, this for the gas phase, kilomole per cubic meter per second per del y. So, this is given to us, and we have been asked the very typical questions. What is number 1? Calculate L min, minimum amount of solvent required, calculate L, which is 1.5 times the minimum solvent required. Our operating condition is 70% of flooding velocity. Based on this, determine the diameter of the column, and the last but not the least, which we are going to decide, which we are going to calculate here, determine the height of this column. So, first 3 already we have answered in our previous lectures. So, we will go very quickly here. Okay. So, and then we have also been given this table to calculate to draw this equilibrium curve. So, this is thermodynamic data, mole fraction 0, 0, 0.562, 0.79, 1.403, we have 2.23, 2.8, we have 6.19, 19.65, we have 68.5, then we have 27.9, we have 104. All right. So, this x in 10 to the power 4, all it means, I leave this as an exercise, you calculate capital X and capital Y as x over 1 minus x, y as y over 1 minus y, and based on this you should be able to draw this curve, equilibrium curve x and y, and if you draw it carefully you will see that there is some convex down here. So, there is some possibility of pinch occurring somewhere here. So, you have to be very, very careful when you draw these curves here. So, let us mark the points here. We have been given 1 and 2, this was our column at location 1 and 2. Okay, we knew x2 pure solvent and we knew y2. So, we can immediately mark this point as 0 for the solvents, and we had this y2 given here 0.00, 0.00333. y1 we know, this also given to us, y1 as 0.111. So, be careful when you plot, not necessarily you have to plot from 0 to 1. For larger resolutions you should work only between the two limits 0.00333 and 0.111. Okay. Now, if we realize that there is a pinch here, we can draw this curve as a tangent. So, wherever it makes a tangent, from there we can get either x1, all right, or we can take the slope as Ls by Gs min. So, whichever way you think is comfortable, you find the slope and then take 1.5 times. The slope would be 1.5 times the minimum, all right. Or you can write down the expressions for this operating curve, and then you can obtain the Ls by Gs operating curve. So, either way it should be able to work. So, if you write down the equations for operating curves, we have Gs y1 minus y2 equals Ls x1 minus x2. So, we know these quantities 41.77, y1 we know 0.11, y2 we know 0.00333, Ls min we have to determine based on x1. So, this x1 based on this tangent where it makes a tangent here will turn out to be 0.00272. So, if you look at very carefully, this is 0.00272 and x2 is of course 0. So, based on this we can obtain Ls min as 1655 kilomole per hour, all right. That means operating curve Ls is 1.5 times Ls min to make it 2069 kilomole per hour. So, idea of doing this exercise is, either you write down the expressions or directly from here, you take, if you know the slope, take 1.5 times the slope, obtain this curve, and you can get x1 operating, which will, you can show that this quantity will be 0.0002174. So, either again you can go back and use these expressions, knowing this new, putting the new values of LS to obtain this x1 as 0.000174. All right. So, the idea is that either use the graph to obtain this x1, or you can go back and put the values of LS to obtain this x1 quantity. So, you should be familiar, we did in the last example earlier case also, that either way, graphical way or the equation will give the same results. So, this is the first part of your questions. Given L min, you have determined L min, minimum amount of solvent required based on this driving force being 0, or wherever it makes a tangent. Based on that, we got to obtain 1.5 times operating curves, we got the new values of x1. So, we have marked all our boundaries. The next is we have to go to hydrodynamics and see there is no flooding, right, there is no loading and flooding there, and it is given that we have to operate at 70% of the operating curves about the flooding conditions, and from that information we should be able to, what is the cross sectional area of the column required to avoid this flooding. All right. So, that will give us g prime kg per second per meter square cross sectional area, and from that we will get the cross sectional area and the diameter of the column. So, let us quickly do this exercise here. Now, if you recall, in that plot we are supposed to get LS by GS. So, first get L at the bottom of the column. Why this also we have discussed earlier, that the flow rate of the liquid is a maximum at the bottom. So, the calculation to be more conservative side, we should do at the bottom of the column. So, at the bottom of the column we have 2069 kilomoles, and then we have 18 water flow rate kg per hour. So, this was the solvent 2069. So, 2069 plus 18 kg per hour, plus we have sulfur dioxide in this. So, how much is amount of sulfur dioxide? Well, we know the GS 4.41.477, that is our GS, multiplied by 0.97, because 97% is removed. So, whatever is removed, it gets into this water phase. So, this is the amount of sulfur dioxide which has gone into this water phase into 64 molecular weight of sulfur dioxide. So, this will be 37529.83 kg per hour of liquid flow rate, maximum flow rate which you have the liquids, right. So, now we can go back and draw this again very quickly. Should recall this curve for loading and flooding, where you had certain quantities on the x, you had certain quantities in the y. You are supposed to mark this curve here, go to this flooding, that will give you flooding conditions. You operate on 70% of this pressure drop. So, when you work on the 70% of this quantity, you will get G prime from here. So, all of this I leave it as an exercise, already you have done this in the previous lecture. This will give us G prime 1921 kg per meter square per hour. So, look at this, now we are getting this kg per meter square per hour. We know this G, total gas flow rate, as 1500 kg per hour. Okay. So, we know G prime here, this will give us cross sectional area as G over G prime, and this will give us 0.781 meter square. From this we get the diameter of the column as 1 meter. All right. So far minimum amount of solvent, operating liquid flow rates, operating conditions, the boundaries, and we got this diameter of this column to avoid this loading and flooding, 70% of this business. Okay, so 70% of the flooding condition. And now we start this very quickly. We do this height of the column based on the number of transfer unit and the height of a transfer unit. Okay, so again we start from here. ZT is NTG multiplied by HTG. This will also be equal to NTL multiplied by HTL. One can also work on overall transfer units at NTOG, then we choose as STOG. One can also work on NTOL multiplied by HTOL. So, there are all 4 different ways of writing this: height of a column, or number of transfer units, or height of a transfer units. Okay. It is up to us. We are careful, you read the problem correctly, what are the quantities which are given to us, because you have to calculate, you have to do this integrations for NTG, and you have to calculate the height of a transfer unit based on this mass transfer coefficients. In principle, any of the 4 equations will work and should give you the almost approximately the same results within this numerical calculations or numerical error. So, here if you recall, the individual mass transfer coefficient for the gas phase and the liquid phase is given to us. So, we should make use of and should work on this NTG and STG. Okay. There is no one can still work on NTOG and S2AG, but the computation will be slightly more cumbersome. Okay. So, first is a very simplest HTG, which we know G prime KY A. Okay. This G prime, again be careful, this is kg mole, this is not kg of loading and flooding graph. So, this is kg mole hour per meter square. This is a place where generally we make a mistake here. Okay. And this G prime varies. So, the question again comes, what G prime we should use in these calculations, because it is not GS. So, as the gas goes through this, passes through the packed bed column, the flow rate of the gas, this kg mole per hour per meter square, it changes as there is a mass transfer from the gas phase to the liquid phase. So, as a very good design or optimum design, one should work on the average at G1 and at G2 at the 1 and the 2 inlet and the outlet of this column. So, we know G1 prime, this is 1, this is 2, this quantity we know, we have calculated earlier, 1921 divided by the molecular weight to give us kilomole per hour per meter square. All right. So, this is what we calculated from G prime from flooding conditions. All right. So, this was the 70% of the flooding limit, from where we got 1921 kg. So, we divide by the molecular weight to make it kilomole per hour per meter square, and G2 prime is nothing but what we have, GS over 1 minus Y2. All right. So, this is solvent flow rate, which remains constant, 1 and 2. So, we have GS over 1 minus 1.2 into 1 over 0.781 to give you the same quantities, 53.66 kilomole per hour per meter square. All right. So, what is this 0.781? This is the cross sectional area we got. So, this was kilomole per hour divided by per meter square, because we know this quantity again, this is the cross sectional area, to make it to give us kilo hour per meter square and kilo per hour per meter square at 1 and 2. From this, if we put simple calculation, this will give us 56.44 as the average mass flow rate based on this empty cross superficial or the cross sectional area of this column. So, we know STG here. So, this we know, this is your G prime. So, we know the G prime, all we have to do is to substitute our expressions, which is G prime over mass transfer coefficients. So, remember, now you have to go back and see what mass transfer coefficient was given to us, which is 270. So, how do we get this 270? It is given 0.075 individual film mass transfer coefficients multiplied by 3600, because this is per hour and what is given in the problem is per second. So, we have multiplied this to obtain 270. This will give us 0.21 meter. So, height of a transfer unit is 0.21. All right. So, that is the simplest quantity we have obtained. If you want to work on S2OG, then remember we have to, if you want to work on this quantity, then we have to do some more calculations here. So, you have to see what the problem is given, so that our calculation is simpler here. So, we obtain STG, now we can obtain NTG. All right. Good. So, now we have to calculate number of transfer units NTG based on this gas phase, individual gas phase. Okay. So, again here if you read the problems, it is given that sulfur dioxide at the inlet is 1%. So, generally we treat 1% as a dilute of very small concentrations, in which case we can make these approximations and we can neglect 1 minus y logarithmic average. So, we write down this NTG expression, simplified form of NTG as dy over y minus yi y2 to y1. All right. So, this is what we are supposed to evaluate, then we can obtain the height of the column Z here. So, this integral is now between y and yi. So, this is the place where it requires numerical integrations. So, you have to pay attention here. How do we calculate this quantity? The best would be to do this graphically. So, we have this equilibrium curve y and x. So, now we are working on a small x and a small y. So, this is the original curve, equilibrium curve, which we can, for example, we can plot like this. Okay. And now, y minus yi, that means we have to obtain operating curve. We have to draw the operating curve. So, what was the operating curve? Operating curve is GS capital Y1 minus capital 1 or small y1 over 1 minus y1 minus y2 over 1 minus y2 equals LS x1 1 minus x1 minus x2 over 1 minus x2. So, in general we can write, replace y1 y2 or x1 x2 with y and x. So, if you do this, you will see that equilibrium curve. Now, it will not be a straight line because we are working on a small y and a small x. So, this would be the equilibrium curve, and this is the operating curve. Note, neither this is linear nor this is linear. All right. So, this is small x and this is y. We have plotted on this, and we have to mark we have to integrate from y2 to y1. Recall, we had this y2 as 0.0033. So, after 97% removal, we had 0.003, and here we have 10% of this inlet sulfur dioxide. So, y1 is given as 0.1. So, we know the limit y2 and y1 dy y minus yi. So, all we have to do is we have to take several small units, right, del y. So, this is numerical integrations, we have to work on del y. So, if you start from here, how do we get yi? Well, you have to take a slope of minus kx over ky. So, this was very first few lectures. We said that from the based on the driving force, we can obtain this yi here. So, this is the interfacial concentrations. Given the bulk phase concentration, what is the interfacial concentrations? Recall the schematics here, y to yi and xi to x. So, xi and yi, and we have y here. So, we have you can take the slope here to obtain this yi. Similarly, you take some other points here. All right. So, you take several data points to obtain all these slopes. In principle, should be parallel, because we assume that mass transfer coefficient do not change along this length. So, take as many as points here between 1 and 2, preferentially should take at least 10 number of points, and then you make a table of given y, what is yi, y minus yi, and of course, you have del y. You make a write down 1, 2, 3, add all of this, perform these calculations to obtain NTG, number of transfer unit, and you should be able to obtain this NTG as around 21.5. So, that was a problem in which we have addressed that we obtain number of transfer unit as 21.5, height of a transfer unit already we have calculated. All right. So, height of a transfer units and number of a transfer units, which is 0.21 meter. So, the total height of the column is 0.21 multiplied by 21.5 meter. So, try to understand this, that entire column is approximately divided. All right. So, we are saying that entire absorption column is divided into 22 units, 21.5 approximately as a conservative design. Height of this column has been divided into 22 small units, and each units we are having a certain degree of rectifications. So, total rectification we wanted starting from 1% to 0.003%. So, from 0.1 to 0.033% we achieve this in a small 22 of such units. Each units we have this fraction of total rectifications, and we require certain height to achieve this. So, 22 units multiplied by height of 1 unit will give us the height of the column. So, this example we have shown 1 minimum amount of solvent required, two operating curves, operating line 1.5, so that we can mark the boundaries. Then we obtain the diameter of the column or the cross sectional area of the column to avoid the flooding, and now we know the height of the columns. Okay, and height of the column we have obtained or we have calculated based on this number of transfer units and height of a transfer unit approach. One can also, since a liquid mass transfer coefficient is also given to us, you must have noticed that in the beginning we said that both Kya and Kxa are given. So, you are most welcome to work on the liquid phase number of transfer units or liquid phase over height of transfer units to obtain very close results. One can also work on overall mass transfer coefficient. Since we know the slope of the equilibrium curve m, one can also in principle can work on overall mass transfer coefficient based on the liquid phase or on the gas phase. Each of this should give the same results. So, as an exercise you can try each of these 4 ways of calculating number of transfer units. Alright. So, this finishes our chapter on absorptions. Maybe we will take a couple of more examples in the next lecture to address some of the issues in the absorption column. Thank you.